Hello, in this video I'm going to show you how to create a spring just like this one using MATLAB. Alright, so the spring is going to be essentially a donut where the cross-sections are displaced in the Z direction vertically. And we're going to define that displacement by constructing a vector. We're going to create a donut. We're going to have we're going to specify the radius that goes from the central axis of the donut to here, which is going to be the inner radius. This is going to be the outer radius, right? And the cross-section here, if you cut the donut here, you'll see that the cross-section is circular. The radius from here to here of that circular cross-section is going to be the outer radius minus the inner radius. Okay, then the cross-section is going to be divided into nodes and all the stuff that we always do in these videos. The inner radius, I'm going to set it as 1. Then the outer radius has to be larger than the inner radius. I'm going to set it to 1.5. Length, because the spring now has a length, right? This is going to be in the Z direction. I'm going to give it a length of 5. I'm going to create a new variable called loop, which is going to specify how many loops I want the spring to have. Another variable that is I'm going to call it fraction or FRAC, because I don't know what else to call it. It's a fraction of a loop in case we don't want exactly 5 loops. We want, I don't know, 5 loops and maybe 20 degrees more. And then the usual number of nodes per cross section. Is at 50, and then the number of cross sections in total, which I'm going to have at 100. Right, so the first things that I'm going to do is to plot the origin, just so I am able to see it. And this is a function that I created in another video. I'll leave the link in the description. Now we're going to define the cross section of the rim. I already specified that is a circle with a radius that is equal to the difference between the outer radius and the inner radius. But before doing anything with that, I'm going to specify a variable called alpha, which is going to be the total angular displacement that these cross sections are going to have, and that is going to be 5 times 360 plus 93 degrees, or 20. I believe we have 20 degrees. So I'm going to do loop, the variable loop, times 360 plus FR AC. Just want to make a little note that is the total angular displacement. Now we're going to create the circle for the rim of the donut. We're going to create the angular vector where all the cross sections are going to be located, and that's going to be using the linspace function that goes from 0 to 360, or in this case to pi because it takes radian values and nodes. Then the radius of this circle, I already said that is the difference between these two values. Half of that, because otherwise we're getting the diameter, right? So it's going to be half of the difference between R out and R in, and we're going to vectorize it right away, which is going to be vector of ones of one row and n nodes columns. That way we ensure that the theta and the radial vectors are the same. We can calculate the z values. Remember that the z-axis is vertical. So we're going to multiply the r that we calculated here, the vector, times cosine theta, and then we're going to do the same thing for y. In this case, we change it to sine. Since this cross-section, the first cross-section is going to be parallel to the YZ plane, that means that x is equal to 0. So we can create zeros. We can give x a value of zeros, length x and nodes. Okay. Now let's plot this. Let's see what we have so far. Sorry, I forgot to put here axis off. Okay, so we have the first cross section, but it's on the central axis of where we want the donut. We have to shift it away by a value. That value is going to be half the radius of this circle plus the R in plus the inner radius. So we're going to add plus R in plus 0.5 times this. And we run it, and yeah, now it is some distance shifted, some distance away in the y direction, which is good. So we have the blueprint right now, and all we have to do is to rotate it right in this plane and then translate it in this direction. Okay, so that direction is going to be the z-axis, so we're going to rotate it and translate it. The translation is going to be done linearly by a variable that I'm going to call dc, and it's going to be a vector uniformly placed that goes from 0 to L, which is going to be the total which is the total length, and it's going to have NC values. Then I am going to create a value of phi, which is the angular displacement. Remember that we are rotating them, so we have to specify angles here. And it's going to be the same, done with a linspace of from 0 to alpha, which is this value here. And it's going to be done over NCS, okay? Now I initialize X, Y, and Z. Okay, so we're going to create a new cross-section. We're going to create a loop that's going to go cross-section by cross-section, and it's going to rotate it and displace it one by one. So it's going to be a for loop. It's going to be I from the first cross-section, right, to the last cross-section, which we don't know necessarily. We can parameterize it and use the NCS. I'm going to create a temporal cross-section here, which is going to be updated every loop. And here to rotate the cross-sections, I'm going to use a rotation matrix, which I have a video explaining what the function does and how to write it and use it. The link is in the description of this video. It basically what it does is takes points in a vector or in a matrix and it just rotates them about an axis. So rotation matrix, I want it to be done over the Z direction, over the Z axis, I'm sorry, by an angle phi, and this is going to be multiplied times X, Y, and Z. Yeah, and remember that this since these we're rotating in 3 dimensions, this is a 3 by 3 matrix, so we need to have a column vector of 3 by 1, otherwise you cannot multiply. And we're going to create a new X matrix where we're going to store in each row one cross section that is already rotated, and it's going to be X, and below that we're going to store the temp cross section, which is going to be the first row. The second row is going to be for Y, and the third row is going to be for Z. Okay, so we do that for Y and Z as well, changing here from the second row and the third row. And now here we can do the displacement. Now we are going to add a value to each of these rows, which is going to be plus, and that value is the one we defined here. So it's going to be dz and the value of the item I. So I have added here a little note that says that is translation in the Z direction. That's where we do that, and we can plot this. Let's see. So plotting each cross section one by one for each iteration. Let's see what we get. Okay. And all right, kind of difficult to see. You can see more or less the shadow of what's going to be the spring, and it looks all right. All right, let's go ahead and create a surface out of this using the surf function. X, Y, and Z. Let's run this. Okay, I actually have no idea what happened. Okay, so I found a mistake. This whole thing needs to go here. All right. Yeah, there it is. Now it works. Okay, yeah, it looks fine. So one last thing to do is the most boring part, is just to cover these holes right here, top and at the bottom. We're going to do a separate function because I don't like mix this process with the other code. It just makes it look messy. So I'm going to call function, create a new function at the bottom. It's going to export the X, Y, and Z matrices with what I'm going to call the plate covering those holes. I'm going to call the function getPlates. It's going to take as arguments all these things. First, we're going to specify the coordinates where we want the first plate to be located at, and the plate is going to be just one point in the middle of the first cross section, and all the nodes in the first cross section are going to converge to that point, effectively covering that opening. So we're going to specify the X, Y, and Z locations for that point, which is going to be right here. So you can see that it is at X and Y is going, X and Z are going to be 0, and Y is going to be the inner radius plus the radius of the cross section. So we can do 0, then Y is going to be the radius of the cross section plus the inner radius, which I probably should have done a variable for that, so I don't have to write all of that, and 0 for Z. Right, the second plate is going to be located right here. And what we can do is just take the first plate or the first point and rotate it by whatever the angle the last cross section was rotated by. So we can use the same rotation matrix. So plate 2 is going to be equal to the rotation matrix around the Z axis by alpha. Now remember, alpha is the total angular displacement, that means this value is going to be the last one as well, the last angle, the angle that the last cross section was rotated by. And this whole thing is going to be multiplied times plate 1, which is a column vector, so it works. Now, running this, each one of these two is going to give us 1 point, and what we need right now is to have it repeated by the number of nodes that the cross-section have. So each node can be connected to that 1 point. So I'm going to do plate 1 is equal to repmat, which is going to repeat plate 1. We just want 1. We don't want to repeat the number of rows, and we want to repeat the number of columns by n nodes. Doing the same for plate 2. Right, doing the same for plate 2. And lastly, we're going to add them to the X, Y, and Z cross section. So our output is going to be already the 3 main cross sections, and it's going to be done like this. So we're going to take the first row from the plate 1, which the first row is going to be for the X coordinates, the second one for the Y and Z for the third row. Underneath we're going to put X, and then we're going to take plate 2 again, the first row. Then for Y is going to be the second rows for plate 1 and plate 2, and Z is going to be the third rows. But this time we're going to shift it by the vertical direction, right, which is going to be 5, and that should be it. Going to uncomment that. This whole thing can be just copied here. Yeah, I'm going to call the function, and I think that's it. Let me see. Oh yeah, it works. You can see now that the openings are covered. Now let's make some tests. So what happens if we change here from 1.5 to 1.1? That they'll make the rim really, really thin. Yeah, you can see there looks almost like a wire. Let's see how many loops. Let's see, 10 loops. Right, so this is for 10 loops. But yeah, it seems to be working. In fact, I like this one, so I might use it for the thumbnail. So in order to export the, I have a video on how to write a script that will turn this into an STL file and also a PLY, and I'm working for an OBJ as well. So this is going to be first a name, which I'm going to call, let's see, spring.stl g there. I'm going to take X, Y, and Z, and then in ASCII, all right. And yeah, here is the spring. Well, it's not the spring that I showed at the beginning, but it's another spring. You can do the one yourself. And here you can see that it's almost, seems there's contact, but it's really, really small. But anyway, if you have any questions regarding this code, I'll leave them on the comment section. I'll do my best to answer them. And yeah, hope this video was helpful to you. Bye.